Hello, welcome to Advanced Composites. Today is the third day of the 10th week of this course. Over last 2 days we had been developing the solution for a plate which was rectangular, simply supported, symmetric in nature, but its D16 and D26 terms were not 0. And what we have found is that if the plate is not symmetric and if the plate is symmetric but its D16 and D26 terms are not 0, then in the first thing what happens is that in the differential equation we get these additional terms which are cosine terms. If the assumed solution for the deflection pattern is sinusoidal, the differential equation also generates cosine terms which are multiplied by D16 and D26, and all that gets reflected in the solution. So, with that understanding, now what we will do is we will start exploring how does the presence of D16 and D26 influence the solution and other stuff related to the plate. Now, in this plate we had said that this plate is simply supported on all the 4 edges, which means that on all the 4 edges moments, respective moments are 0. So, on the edge x is equal to 0 and x is equal to a, mx is 0, and on edges y is equal to 0 and y is equal to b, my is 0. Let us see what our solution gives us. So, we have figured out how to calculate W11, W12, W21 and W22. Now, if we want to compute mx, we know that mx is equal to minus d11 del 2 w naught over del x square minus d12 del 2 w naught over del y square minus 2 d16 del 2 w naught over del x del y. Okay. And here w naught x y is equal to sum of w mn sin m pi x over a sin n pi y over b. Okay. And we can find these coefficients w mn exactly by using the process which we had described earlier. We have developed the process for a 2-term solution, but we can extend the same process for solutions which have 3 terms or 4 terms or whatever, and as we increase the number of terms, our solution is going to get more and more accurate. So, if I plug in this relation back into the expression for mx, what do I get? So, I get mx is equal to, so this sine term is getting differentiated twice. So, I get d11 m pi over a whole square plus d12 n pi over b whole square, and this thing is multiplied by sine m pi x over a sin n pi y over b, and then now we have a d16 term. So, I have minus, so the negative sign here, this negative sign and this negative sign, they disappear because this thing is being differentiated twice. So, I get sine, then I get cosine, and when I differentiate cosine, it becomes negative, right, and same thing happens here. So, actually I should still have a negative sign here, right. So, I get one negative sign because I am differentiating this twice, yes, so I am sorry, so this becomes positive. Now when I differentiate this w with respect to x and y, there is no reversal of sign because sign just gets differentiated into cosine. So this negative sign remains and I get 2 D16 m n pi square over AB cosine m pi x over A cosine n pi y over B, okay. And this entire thing I have to sum up over the index m and n. So this is what I get. Now let us look at the value. So what is the value of, so if D16 was 0, in case D16 was 0, that is each ply was orthotropic in nature. If D16 was 0, then mx would be 0 at x is equal to 0 and also at x is equal to a, because if D16 was 0, then this term does not exist and sine terms vanish at x is equal to 0 and at x is equal to a. So mx condition is satisfied. Similarly, if we want to compute my, we will find that my, if D26 was 0, it will remain 0 on y is equal to 0 and y is equal to b edges, okay. But if D16 is not 0, if D16 is not 0, then what happens? Then mx is equal to minus 2 D16 m n pi square over AB cosine m pi x over A cosine n pi y over B, and what is its value? It at x is equal to 0, it will be minus 2 D16 m n pi square over AB, and if x is equal to 0, then its value is cosine n pi y over B, because yeah, so this is at x is equal to 0. And this is equal to minus 2 D16 m n pi square over AB cosine m pi y over B, and this will be plus minus at x is equal to A, because if at x is equal to A, what is the value of cosine mx over A? It will be cosine m pi. So suppose m is 1, then it will be negative 1. So this negative 1 will get multiplied by minus and it will become a plus. If x is m pi over and at if m is equal to 2, then it will be cosine 2 pi, which will be 1. So this will oscillate anyway. So at x is equal to 0, what is the shape of mx? So this is 0. So this is x, suppose this is x is equal to 0 edge. So actually so suppose I am doing y on x on this axis, and this is 0 to b. So it will be and here if I am plotting mx, and this is I am plotting at x is equal to 0. So, it will be this sort of thing. So, it will be something like this. I am just plotting the magnitude, okay, and it depends on the value of n. So, if n is equal to 1, then it will be pi y over b, cosine pi y over b. So, it depends. So, it can do this, but anyway the point is that it will start from some maximum value and it will end at the same maximum value. It can do this also, and so on and so forth. Okay. So, what we see is that mx is not equal to 0 at x is equal to a and at x is equal to 0. Similarly, we see that we can show that my is not equal to 0 at x is y is equal to 0 and y is equal to b. So, this is what computation tells us. So, this is the result for computation. Results from calculation. So, calculation tells us that mx and my are not 0 at the simply supported edges, but these edges are simply supported. So, it has to be 0, right. So, we get the solution or the calculation of mx, we get an error. Okay. So, this difference between actual value and the computational value, there is a difference, and this thing is known as the edge effect. This is known as edge effect. Okay. And the magnitude of mx, so suppose and on the edge it will vary from point to point. So, suppose its maximum value is something mx max, this magnitude, this reduces as number of terms in solution goes down or goes up. Okay. Same thing is true for my also. The value of my max on edges y is equal to 0, y is equal to b, it reduces with increasing number of terms. Okay. So, this is there, and typically we say that this is in a reasonable border if mx max on edge is divided by mx max. So, actually here I will say edge, and this is also I will say edge. So, mx will have a maximum value on edge and mx will have an even higher value somewhere in middle of the plate. Okay. On edge it will be small, but it will be non-zero, and but in the plate if you compute somewhere here the bending moment will be maximum. So, okay. So, mx will be maximum here. So, that is what I call mx max, and mx is maximum on the edge, and that maxima I call as mx max edge. Okay. So, if this ratio is typically, if it is less than 1, if this ratio, so if we keep on increasing the number solution till this ratio becomes less than 10%, then we say then we can say that results are reasonable. reasonable. Okay. So, this problem appears in analytical formulations like we did it using the special Galerkin method, or even if we try to do the same thing in finite element analysis, we again come across this edge effect, and it comes in again and again. Okay. So, this is a very important feature, and because of this we tend to get some artificially high stresses also on the edge, which may not necessarily be there in the real plate, because in the real plate there are no moments on the edge, on the edges. So, this is one feature or one artifact which comes up because of D16 and D26. So, another thing is related to the position of the values of mx for at different locations, and how those vary as we introduce the terms D16 and D26. So, that is another thing we will look tomorrow, and we will continue this discussion on D16 and D26 tomorrow as well. So, thank you, and I look forward to seeing you tomorrow. Bye.